This section is part 2 of our journey through L'Hopital's rule, and we'll round it up with the growth rates. So in this section, we're going to identify indeterminate, I guess I need to correct my spelling, indeterminate forms produced by quotients, products, subtractions, and powers, and apply L'Hopital's rule. So what we've done so far, we've looked at the cases that was like a 0 over 0 or infinity over infinity, and we found ways to deal with that. Now we're going to look at a 0 times infinity situation, an infinity minus infinity situation, a 1 to the infinity power, infinity to the 0, and 0 to the infinity. We'll be looking at several different types here, and determine if it's going to converge, or if it goes to infinity, goes to a number, goes to 0, and so on. So that's what this section is about. We're going to use these tools from L'Hopital's rule, but we just take a little bit of a different approach at it. We can be creative here. It's kind of fun. Okay. So let's look at this form here, the 0 times infinity situation. Now, L'Hopital's rule works if it's a 0 over 0 or infinity over infinity. So if we can make this instead, use our skills in algebra and treat this as infinity over 1 over 0, that's like saying an infinity over infinity situation. So that's one of the approaches. Or you can say it's 0 over 1 over infinity, and that'd be like a 0 over 0 situation. So we look at doing one of the two of these to resolve this issue. So let's get to an example here. Evaluate the limit as x goes to 0 from the right side of x natural log of x. So we can treat this as the limit as x goes to 0 from the right side of our natural log of x. It's just natural log over 1 over x. So that 1 over x, if you evaluate that, would come back up to the top being x natural log of x. So now we do have an infinity over infinity situation, because as x approaches 0 from the right side, natural log of x is negative infinity, and then down below we have 1 over 0 from the right side would be an infinity. So now we can apply L'Hopital's rule. We have the limit as x goes to 0 from the right side of 1 over x over negative 1 over x squared. And now if we work with the algebra a little bit, we have the limit as x goes to 0 from the right side of, that's 1 over x times the reciprocal of the denominator, so let's say negative x squared over 1. So we have the limit as x goes to 0 from the right side of, now it's a negative x squared over an x, so that's just a negative x, and that's going to be 0. So we're all good there. So it's a 0 times infinity situation, and it comes out to be a 0. Next one, limit as x approaches 0 of x cotangent of x. So when I first did this problem, I'm like, okay, let me try the same thing, but I realized really quickly I need to go a different direction. And the fact that we have this cotangent lets us do that, because cotangent has a reciprocal. So the limit as x goes to 0 of x cotangent x can be written as x over 1 over cotangent of x. And 1 over cotangent of x, everyone, what is it going to be? You're right, tangent x. So as we apply that, that's on infinity, it's a 0. As we apply the 0, then we would have a 0 over 0 situation. So if we take L'Hopital's rule and apply it, we have the limit as x goes to 0 of 1 over secant squared x. So if we apply the 0 now we don't have an indeterminate form, so it's going to be 1 over secant of 0 quantity squared. So it's 1 over 1 squared, 1 over 1, which is 1. Okay. Now we'll look at the form that's an infinity minus infinity. And this is typically going to be like a fraction that we have to combine, get a common denominator, combine the numerators. Then we have a numerator and denominator that will typically be an indeterminate form. Okay, so here we go. The limit as x approaches 0 from the right side of 1 over x squared minus 1 over tangent. So there's really no quick and easy way to do this. Just call this x squared over x squared on the right term, and then the other first term we have a tangent x over tangent x. So what we have is the limit as x approaches 0 from the right side of tangent x over x squared tangent x minus x squared over x squared tangent x. Okay, so now we're going to, if we look at this, we can combine the numerator. We have the limit as x approaches 0 from the right side, so we have the same denominators, is tangent x minus x squared over x squared tangent x. Now given the tangent of 0 is 0, 0 squared is 0, we have 0 minus 0 over 0 times 0, so it's a 0 over 0, the indeterminate form. So we can apply L'Hopital's rule, and we'll end up with the limit as x goes to 0 from the right side. The derivative of tangent is secant squared x. Derivative of x squared is 2x. Now down below we have a product rule situation, so it's going to be 2x tangent x plus x squared secant squared x. Now if we put that 0 in here, secant of 0 is 1, so you have 1 minus 2 times 0 is 0, so 1 minus 0 is 1 on top. And then down below we have 0 times 0 plus 0 times 1. So it's a 0 over 1 situation. So we have, if we put in that 0, it's going to be secant of 0 squared minus 2 times 0 over 2 times 0 tangent of 0 plus 0 squared times secant of 0 squared. And that's going to be a 1 over 0 situation, which is infinity. So doing this doesn't mean you're always going to have a nice number answer, but it does mean you can find out what it's going to be, the limit. Okay, moving on. Here's another one. So we'll multiply the first term by sine x over sine x, and the second term by x over x. So we have the limit as x goes to 0 from the right side of sine x over x sine x minus x over x sine x. So we have the limit as x goes to 0 from the right side of sine x minus x over x sine x. So again, if you apply the 0, everything is 0. You know, got a difference of zeros on top and 0 times 0 on bottom. So now we can apply L'Hopital's rule, and we have the limit as x goes to 0 from the right side of cosine of x minus 1 over, now we have a product rule, 1 times sine x plus x times cosine of x. And just looking at that, we have cosine of 0 is 1, so it's 1 minus 1 on top, over 1 times 0, sine of 0, 0, plus 0 times cosine of 0 is 1. So it's really just a 0 over 0 still. So we can take and apply L'Hopital's rule again. It's going to be kind of a long expression here. Let's get going with it though. It's going to be a negative sine x on top. But on bottom, we're going to have derivative of sine is cosine of x. Then we have plus, now it's in the product rule. Derivative of x is 1, so 1 times cosine of x. And then plus x times derivative of cosine is negative sine x. So now in the numerator we have a 0. In the denominator we have cosine of 0 is 1, cosine of 0 is 1, but then the sine of 0 is 0 and x is 0. So we have 0 over 2, which is then 0. Okay. Now we're going to look at a situation when you have, infinity to the 0 power. When you have a power situation, you could take advantage of our laws of logarithms and evaluate it this way. So in a case like this, you have x to the 1 over x as x goes to infinity. So it's infinity as a base. It's 1 over infinity is 0, so it's infinity to the 0 power. So we can say y equals this x to the 1 over x. If that's the case, then taking the natural log of both sides would give us natural log of x to the 1 over x, or 1 over x times the natural log of x, which could be represented as natural log of x over x. So if we look at the limit as x goes to infinity of the natural log of x over x, I have infinity on top, I have infinity on bottom, so it's an indeterminate form. So I can take L'Hopital's rule here, and I'd have the limit as x goes to infinity of 1 over x over 1. And if I work with that a little bit, that's just going to be 1 over x. And as x goes to infinity, that's going to be 1 over infinity, so it's 0. And we're not finished yet, because what we're seeing is the limit of the natural log of y as x goes to infinity was 0. So you can write that as natural log of the limit of y as x goes to infinity is 0. And if you make both sides powers of e, you can cancel that natural log in front, and you'd have the limit as x goes to infinity of y equals e to the 0, which is 1. And that's what our limit is. The limit as x goes to infinity of infinity to the 0 power, no, sorry about that, of x to the 1 over x, let's get a little excited there, it's going to be 1. And what got me excited was that infinity to the 0 power in this case is 1. And what's important is just to realize infinity is not always going to be the same infinity. So there are different times that it could be different results. And just understand that infinity is not a defined value. It's technically undefined. So for example, there's an infinite number of even numbers and there's an infinite number of whole numbers. But there's twice as many whole numbers. So think about that. Infinities aren't always the same. Let's try this again. It says evaluate the limit as x goes to infinity of x to the 1 over natural log of x. So we have an infinity to the 0 power again. So again, I'm going to come up here and just say y equals x to the 1 over natural log of x. So the natural log of y is the natural log of x to the 1 over natural log of x. So this becomes a coefficient. I just laugh because of this. It feels like we're like in kind of a loop. It's going to be 1 over the natural log of x times natural log of x, which is natural log of x over natural log of x. Okay. So when I did this one, I just kept working it out, but a student of mine in class pointed out, well, the limit as x goes to infinity of the natural log of x over the natural log of x. He was saying, isn't that just 1? I'm like, yeah. I mean, I carried it further because I took this to be the limit as x goes to infinity of 1 over x over 1 over x, which becomes the limit as x goes to infinity of x over x. And if I apply L'Hopital's rule again, I have the limit as x goes to infinity of 1 over 1. Oh, 1, not x. Which is 1. So he was right, but part of me just felt like I was taking a shortcut. Okay, so what this means is the limit of the natural log of y equals 1. So natural log of the limit as x approaches infinity of y is 1. So that e to the natural log of the limit of x approaches infinity of y is e to the 1, so that would cancel. So we would say that the limit as x approaches infinity of y is e to the 1, which is e, or the limit as x approaches infinity of x to the power 1 over natural log of x is e. So what's really interesting about that, so this is another infinity to the 0 power, but you see this one actually with the limit process gives us an e, where the previous one gave us a 1. And we'll go up there all the way. Okay, now we have the case 0 to the 0 power. We'll look at that. So we have the limit as x approaches infinity. Sorry, as x approaches 0 from the right of sine of x. So again, we'll say y equals x to the sine x. So natural log of y equals the natural log of x to the sine x. So this becomes a coefficient. So the natural log of y equals sine x times the natural log of x. Okay, so I'm going to look at this limit as x goes to 0 from the right side of natural log of x over 1 over sine x, which is to say it's the limit as x goes to 0 from the right side of natural log of x over cosecant x. So the trig functions are pretty helpful because you can move them there, and then it's an reciprocal function, so you can always make that substitution. It doesn't look like you have a fraction to deal with. Okay, so we're going to use L'Hopital's rule, and we have the limit as x goes to 0 from the right side of the 1 over x over, and the derivative of cosecant x is negative cosecant x cotangent x. So we end up with the limit as x goes to 0 from the right side of 1 over x, I got the negative out front, negative x cosecant x cotangent x. Okay. Now we can play with this a little bit and treat this as the limit as x goes to 0 from the right side of, and I have a strategy here, so trust me with this, 1 over negative x times, and cosecant is 1 over sine x, and then cotangent is cosine of x over sine x. So if I did that, I'd be able to say this is the limit as x goes to 0 from the right side of, bear with me now, sine x over x, and we've seen this before, times sine x over cosine of x. I have a negative to put somewhere. Why don't we just put it out front, So we end up with negative limit as x approaches 0 from the right side of sine x times the limit as x approaches 0 from the right side of sine x over cosine of x. And that's going to give us, this is sine x over x, excuse me. We've seen the sine x over x limit as x approaches 0 to be 1. We've worked that quite a bit, even back in our early days of the class. And then limit as x approaches 0 of sine x over cosine x is sine of 0, which is 0, over cosine of 0, which is 1. I've got a negative out there somewhere, but that's irrelevant because it's just 0 in the end. But again, we're not finished yet, because that's saying that the limit as x goes to 0 from the right side of the natural log of y equals 0. So the natural log of the limit as x approaches 0 from the right side of y equals 0. If we make both sides powers of e, we have the limit as x approaches 0 from the right side of y equals 1, or the limit as x approaches 0 from the right side of, this was an x to the sine x equals 1. Okay, so that's a 0 to the 0 that becomes a 1. I just want to be cautious. Don't jump to the conclusion that that means that all 0 to the 0s are 1. Okay, moving on. Got a couple more problems in this section to do. Here's the limit as x approaches 0 of x to the x. So again, we can say y equals x to the x, and natural log of y equals natural log of x to the x, where this x can become a coefficient. So it's x natural log of x. Or we can treat that as natural log of x over 1 over x. So if we take the limit as x approaches 0 from the right side of the natural log of x over 1 over x, we have negative infinity over infinity, so it's going to be, taking the L'Hopital's rule applies, so limit as x goes to 0 from the right side of 1 over x over negative 1 over x squared. So that's going to be the limit as x goes to 0 of a negative x squared over x, because you multiply by the reciprocal. So that becomes negative limit as x goes to 0 of x, just of an x. So that's from the right side. That's going to be 0. So again, we have the natural log of y, the limit, as x goes to 0 from the right side of natural log of y equals 0. So natural log of the limit as x goes to 0 from the right side of y equals 0. So e to those as powers becomes the limit as x goes to y, x goes from 0 from the right side of y equals e to the 0, which is 1. So we could say the limit as x goes to 0 from the right side of x to the x equals 1. Okay, we have one more to do. This one didn't print, so I'll write it out. It says we have the limit as x goes to pi over 2 of 4 cosine of 3x times secant of negative 7x. Now, those of you who've had me in trigonometry, or anyone else in trigonometry that's done it, probably want to combine those, but we're not going to do that. We have the limit as x goes to pi over 2 of 4 times cosine. And why don't I take that 4 and put it out front? So it'd just be cosine of 3x over, and so this secant could be written as a 1 over cosine of negative 7x. So now we have, putting pi over 2 in there, in 0 for 0 case, we can apply L'Hopital's rule. We have the 4 times the limit as x approaches pi over 2. And the derivative of cosine is negative sine, so it's going to be negative 3 sine of 3x. That negative 3, the negative, because the derivative of cosine is negative sine. The 3 because of the chain rule, that's from the derivative of the 3x over, we have a negative of negative 7 times cosine, no, it's times sine of negative 7x. So we have 4, in fact, let's get that limit from up top, out front. 4 times the limit as x goes to pi over 2 of 3 sine of 3x over 7 sine of negative 7x. Now, we're putting a pi over 2 in here, so this is essentially going to be negative 4 times 3 sine of 3 times pi over 2 over 7 times sine of 7 pi over 2. Now, I think we all know what 3 pi over 2 is, what sine is of that. That's just down here. So sine of 3 pi over 2 is -1. How about -7 pi over 2? So -7 pi over 2 -7 pi over 2. So that's going to be going the opposite direction. So that's -pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So it's up here where pi over 2 is. So that's just going to be +1. So this limit would be -4 times 3 times -1 on top over 7 times 1 on bottom. Those negatives cancel. It gives us 12 over 7. And that's it. And that'll do it, I believe, for this section. Okay. Now after this, you can click over to the growth rates one.